In this video, we're going to begin section 6.2, which is entitled Using the Normal Distribution. This lecture will be dedicated to defining what the normal distribution is, getting an idea of some of its characteristics, and then doing just a couple of the most basic types of examples of finding probabilities with a normal distribution. Okay, let's begin with the definition, and before I click to it, I'm going to warn you that the definition I'm starting with is very technical. We're going to steal a couple of ideas from it, but I don't want you to get too hung up on the nasty formula you're going to see. Again, don't freak out about that function. Let me read it to you first. The normal distribution is a continuous probability distribution described by the function, and I'm not even going to read it because this isn't really the focus of this slide. I know your eyes are going to be drawn to it, but I don't want you to focus on that. We're going to talk about characteristics of the normal distribution that allow us to avoid this. We're also using the calculator in this class, and so the calculator will take care of all that nastiness for us. Here are the two things I do want to point out about the normal distribution. One, it's a continuous probability distribution. The binomial distribution, and in fact all of Chapter 4, was dedicated to discrete probability distributions, and now we're dealing with a continuous probability distribution. So we'll be looking at scenarios that we couldn't handle in the previous chapter. The other thing I want to point out is that the function that we're using depends on the mean mu and the standard deviation sigma. You'll notice that there's a mu and a couple of sigmas in the formula. Both mu and sigma have a role in the shape of this distribution in the pattern of variability. We'll talk about what that role is outside of the context of this formula. We're just going to state them as facts. It turns out that this function is what gives us the bell curve shape that defines the normal distribution. The normal curve is a bell-shaped curve. I've drawn this curve here, and it's not perfect because I drew it by hand. I didn't draw it with technology. But it gives you a basic idea of what that function's graph would look like. This is what the normal distribution looks like. The data is denser in the center, there's less data on the ends, and it turns out that the mean is dead smack in the center, and that's the role of the mean in the graph of this function, is that it falls right in the middle. Let's look at a list of the characteristics of the normal curve. Rather than talking about it so abstract, let's just get a list of facts about the normal distribution, and that's what we'll use instead of looking at that nerdy function. So here are some characteristics of the normal curve. First, it's bell-shaped, which we already said. That disgusting function gives us a bell-shaped curve. Second, it's symmetric about its mean. Now, I showed you that the mean was in the middle. What I didn't say, and what you can't really tell from my graph because it's not perfect, is that that's a line of symmetry. The left half and the right half of the graph should look exactly the same. And I know mine doesn't, but a true normal distribution would. So the graph is symmetric about its mean. The third characteristic is very important for the applications we want to do in this class. The total area bounded by the curve and the horizontal axis is 1 unit, whatever the units are. So if we were to shade the area underneath the curve, but bounded below by the axis, that total area approaches 1 square unit the further and further you move out. The further you shade onto the edges from the center, the more area you get, and that total area is 1 unit. Because we're going to be doing probability examples, that 1 is like 100%. It's like that maximum possible probability. So we're going to have this link between area and probability, and that's why that characteristic is important. Fourth, the ends extend infinitely, approaching but never touching the horizontal axis. I can't draw it this way, but the end of this curve doesn't really stop here. I've truncated the graph. It actually extends forever and ever and ever, and it does the same thing on the left side. Those edges get closer and closer to this horizontal axis, but they'll never actually touch it. So there is no lower bound or no upper bound to the normal curve. It extends infinitely in both directions. We'll use that fact when we get into the more complicated examples in a future video. And then finally, just a fact about the effect the standard deviation has on the graph. The larger the standard deviation is, the flatter the curve will be. So we have no frame of reference here because I only have a single graph. So you can't tell just by looking at this one picture. But it turns out that the standard deviation affects how tall and skinny the graph is, or if it's more flattened out. A normal distribution with a small standard deviation will be tall and skinny. And a normal distribution with a large standard deviation will be wide and flattened out. The total area under both curves is 1. There's just more area concentrated in the center when the standard deviation is small. And that should make sense in the context of what a standard deviation tells you. It tells you how varied the data is. So when the standard deviation is small, the area is all compacted together. All of the data is very close. And when the standard deviation is large, the data is more spread out. So the graph will look more spread out. So there's a logic to it, but that's the effect that the standard deviation has. The larger the standard deviation, the flatter the curve will be. So in talking about this third characteristic, I mentioned that the area and the probability were linked. To find the probability that a normal random variable falls on a certain interval, we find the area bounded by the curve and the horizontal axis over that interval. If I had a normal distribution and I wanted to find the probability that the value of the variable fell between this number, which I'll call A, and this number, which I'll call B, I just need to find the area bounded by the curve, the horizontal axis, and those two vertical line segments that I drew. We'd be looking for this area right here. And it might seem strange that I'm saying that so nonchalantly, because how could we possibly find that area? Well, it turns out that you find that area using that nasty function that we had before. But that function's really complicated, and furthermore, you don't really just use that function, you have to do calculus on that function. That's well beyond anything we want to do by hand, and so we're going to learn how to do this with the calculator. The calculator has a function that will allow us to find these areas. So what do we call that calculator function? It's called normalcdf, and it requires 4 inputs. Normalcdf of a, b, mu, sigma is the area bounded above by the normal curve with mean mu and standard deviation sigma, and bounded below by the horizontal axis on the interval from a to b, where a is less than b. So going back to the picture I drew on the previous slide, as long as we knew the mean, which is important because that's what the center of the graph is, and as long as we know the standard deviation, which I can't mark on the axis because it's not going to be in a specific spot on the graph, but it does affect the height of the curve, so I just kind of note it off to the side. As long as we know those two things about the graph, we can use the calculator function to find any area between two bounds A and B. A is the smaller bound, B is the upper bound. It's important that you put them in that order. A is less than B. Lower bound first, upper bound second. Let me show you another picture that's a little bigger here. So if I want to find the area between two bounds A and B in a normal distribution with mean mu and a known standard deviation sigma, I do normalcdf of A, B, mu, sigma. Lower bound, upper bound, mean, standard deviation. Let's look at an example. A machine is designed to fill jars with spaghetti sauce. The amount of fill is a normally distributed variable with a mean of 850 grams and a standard deviation of 5 grams. Find the probability that a jar selected at random has between 845 and 855 grams of sauce. Okay, so this is going to be an example that uses the new calculator function. But why? Why do I know that? Notice that this isn't a binomial problem because we're not looking at a number of successes and a number of trials. Instead, we're specifically told that this variable is normally distributed. And so I'm looking at an application of a normal distribution. I'm told the mean and the standard deviation are 850 and 5 respectively. And then I'm asked to find the probability that the random variable falls on some interval. That's exactly what this normalcdf function does. If you tell it the interval, the mean, and the standard deviation, it will find the area, and that area is the probability. My advice when doing these problems is to draw the picture. You want to draw the picture associated with the area that you're finding. So first I would draw a horizontal axis, and then I would draw a normal curve above it. And don't worry about how tall it is or how short it is based on the standard deviation. We're not drawing on graph paper, so there's no frame of reference. So just draw any normal distribution. The center of that distribution needs to be the mean. So we know the mean is 850. The standard deviation is important for the calculation, but it's not something that you mark on the axis. Like, it doesn't matter where it falls on the x-axis. So I like to write that off to the side. The problem said that the standard deviation was 5. So I'm going to write a standard deviation of 5 off to the side. And now let's go back to the problem and make sure we remember what we're being asked to find. Find the probability that a jar selected at random has between 845 and 855 grams of sauce. So don't worry about getting it exactly right. 845 is going to be somewhere to the left of the mean because it's smaller than the mean. 855 is going to be somewhere to the right. It should be the exact same distance, but again, that's not the point of the picture, so don't try to get it perfect. Just make sure you get everything in the correct relative position. The numbers should be in order from smallest to largest on your axis. What we're looking for is the area bounded by those two curves. So I like to shade that in. And now I ask myself, do I have a way to find this area? Yes, that's what normal CDF is built to do. Normal CDF of A, B, mu, sigma is the area bounded above by a normal curve with a given mean and standard deviation, bounded below by the horizontal axis on an interval from A to B. We know the mean, we know the standard deviation, so we have this upper bound of the normal curve, and we have this interval from 845 to 855. This is exactly what normal CDF is built to do. So I'm going to do normal CDF of 845, that's the lower bound, 855, that's the upper bound of the area, the right bound of the area. The third input is the mean, 850, and the last input is the standard deviation, 5. Lower bound, upper bound, mean, standard deviation, or the way that I like to say it is A, B, mu, sigma. A is the lower bound, B is the upper bound, mu is the mean, sigma is the standard deviation. Now all we have to do is put this into the calculator. Again, there is a way to do this by hand that uses that nasty function, but it requires calculus. So we're not going to do it that way. We're just going to rely on the calculator. Just like with binom PDF and binom CDF, I'm going to have to do this two different ways at first to show you the two different operating systems. Let me start with the newer one with the input screen. Normal CDF is found on the same screen as binom PDF and binom CDF. If you push second vars, you'll see normal CDF as the second option. There's also a normal PDF, which we will never use. Normal PDF tells you how tall the normal curve is. How tall the curve is won't be of interest to us. All our problems will revolve around areas. So we'll use normal CDF, and we will learn the one underneath it, inverse norm, but we'll never use normal PDF. So we want choice 2. You'll notice that the input screen doesn't call these A and B, it literally says lower and upper. Lower bound, upper bound, mean, standard deviation, and then the paste option, just like you saw with the binomial functions. Our lower bound was 845. Enter. Our upper bound was 855. Enter. Our mean was 850. Enter. Our standard deviation is 5. And then when we hit paste, that will put that on our main screen. And we just have to hit enter one more time to get our result. If you're familiar with the empirical rule, you can guess what this answer is. Since 845 is one standard deviation below the mean and 855 is one standard deviation above the mean, the empirical rule tells us that this will be around 68%, 0.68. And when I hit enter, you'll see that I get an answer really close to 0.68. Just like with the binomial functions, I'm going to require that you show me your calculator input. And so I don't care how many decimal places you give me, 2, 3, 4, those are all okay. Just a couple of sig figs. So I'm going to go out to 0.683. That's 68.3%. So in all of that talk, it might be easy to forget what this answer was supposed to be. We were finding the probability that one of these jars has between 845 and 855 grams of sauce. We said that that probability is 68.3%. Another way to interpret that is that 68% of all such jars fall in that interval. Most of them, over 2/3 of the jars, have between 845 and 855. Let me rework this without the input screen. You're going to go to the same spot, second vars. It should still be choice 2 in your calculator, so pick choice 2. And you'll notice instead of getting an input screen, we just get a prompt on our main screen, and we have to put in the inputs in the correct order. It's lower bound first, so the lower bound of our interval was 845. Then you type a comma. It's upper bound second. Our upper bound was 855. Then you type a comma. The mean always goes in the third spot. The mean of the distribution was 850 grams. Then a comma. The standard deviation always goes in the last spot. The standard deviation was 5. Hit enter, and you get the same result. Just like with previous functions, I'm going to demonstrate this method more often because the input screen makes it a little more intuitive how to do it. With this version, you have to know the order of the inputs, and that will give me an excuse to remind everybody of the order of the inputs if I do it with this version. Let's look at another example. The time it takes to complete an NBA game is normally distributed with a mean of 136 minutes and a standard deviation of 7 minutes. Find the probability that a randomly selected NBA game is between 120 and 130 minutes long. Okay, so again, let's approach this from scratch. Let's pretend like we're on the exam where all of the problems are mixed together, and we have to decide how we're going to approach this. What is the key clue that tells us that we're going to use this normalcdf function here to find this probability instead of one of our previous techniques? It's the fact that it specifically tells us that it's normally distributed. That's a pretty big hint. So we know that this data follows a bell-shaped distribution. We know the mean and the standard deviation, so I'm going to draw that distribution on another slide. Bell curve. Again, don't worry about drawing it perfectly. Mine doesn't look great. It's just for reference to help us see how to set up the calculator function. We know the mean is 136, so I'm going to put that in the center of the distribution. The standard deviation is 7 minutes. I'm just going to write that off to the side a little bit. It's not something that you need to mark on your graph. It does have something to do with the shape of the graph, but again, we're not trying to make this perfect. We're just using this for reference. Let's go back to the problem. We're looking for the probability that the game that we select at random is between 120 and 130 minutes long. I'm going to mark those on my graph, and you'll notice this time they're both on the same side of the mean. 130 is also smaller than the mean. So the area we're finding is restricted to just this piece on the left side of the graph. But that doesn't change how we do it. We still have a piece of area that's bounded above by a normal curve with a given mean and standard deviation, bounded below by the horizontal axis, and between two known bounds. It doesn't matter that they're both on the left side of the mean. Normalcdf will still handle this. Normalcdf just needs to know what is your lower bound, what is your upper bound. Tell me the mean, tell me the standard deviation, and I'll give you the area bounded by that curve in the axis. So we're going to use the normalcdf function. The lower bound of our area is 120, and the upper bound is 130. That's where the area stops on the right side. The mean is 136, and the standard deviation is 7. The mean always goes in the third spot. The standard deviation always goes in the fourth spot. Now, unlike the previous example, we couldn't even use something like the empirical rule to get an idea for what this area should be. About the only thing we can say with what we know is that the amount of area is going to be less than 50%. Clearly, we've shaded in less than half of the graph because we only have a slice on the left side of the mean. So the answer is going to be less than 0.5, but other than that, we don't really know enough to say where it's going to fall. Remember that our picture isn't perfect, so you can't base it on how much area I shaded in the graph. So we're going to hit second vars. Choice 2. Normalcdf is choice 2. Our lower bound was 120. Our upper bound was 130. Our mean was 136. And our standard deviation was 7. And we see we do get an answer smaller than 0.5. It's much smaller than 0.5. It's about 0.185 if I round to the nearest thousandth. And that's around 18.5%. So this means you have just under a 20% chance of a randomly selected NBA game being between 120 and 130 minutes long. And again, another way to interpret this is to say that around 18.5% of all NBA games fall in this interval. We're thinking of it from the terms of probability, but it's also just a proportion of all of the data that falls in that range. One more example of this type. They're all pretty much the same once you get the hang of it. You just have to identify the type of problem that you're doing and get used to the calculator function. The heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected woman is between 65 and 68 inches tall. Okay, there's that key phrase again. We're specifically told that this data is normally distributed. So I know that the data is going to fall into a bell-shaped pattern. I know the mean and I know the standard deviation, so I can mark that when I draw my curve. The mean is 63.6. The standard deviation is 2.5. Go back and make sure I know what I'm being asked to find. Find the probability that a randomly selected woman is between 65 and 68 inches tall. 65 and 68 are both bigger than the mean. And 65 probably isn't exactly right there, and 68 certainly isn't exactly right there. But we're just trying to get everything in the correct relative positions. The numbers are in numerical order from smallest to largest. We want the area bounded by the curve and the axis between those two spots. This is what normal CDF is built to do. We're going to use normal CDF, which I'm going to start abbreviating NCDF. And the order of the inputs is lower bound, upper bound, mean standard deviation. I know 63.6 is the smallest number that I marked on the axis, but that's not the bound of our interval. The lower bound on our area is 65. The upper bound on our area is 68. Then we put in the mean, which is 63.6. And then we finish with the standard deviation, which is 2.5. Lower bound of the interval or of the area, upper bound, mean standard deviation. The axis normal CDF, it's second vars, choice 2. Lower bound of our area was 65. Upper bound of our area was 68. The mean was 63.6. The standard deviation was 2.5. And we get around 24.9%, 0.249 if we round to the nearest thousand. Again, I'm not super concerned with where you round to, just give me a few decimal places. This is 24.9%. The probability of selecting a woman in this range is right around 25%, right around a quarter. Which means that about 25% of this population is between 65 and 68 inches tall. In all of these problems, we're finding the area between two bounds, and that's what normal CDF is built to do. So these are the easiest examples. I don't think we need to do any more of these. In the future, we're going to look at some examples where we're not going between two bounds, and those take a little more work. That's the kind of stuff we'll be looking at in the next lecture. If you have any questions about using normal CDF or anything else in this video, reach out to me and let me know. I'll do my best to clear things up.